We're given a small circuit diagram, looks like an RLR circuit, and we have voltage input and we have voltage output. So we have these two voltages, and we have the resistor 1, an inductor, and resistor. Now we're going to want to do this in the S domain, so we need to convert this inductor into the S domain. We know that Z of L is equal to S times L. Now I'm just going to leave this in symbolic form, and this is until we need to actually write this out right here. So for A, I'll write this right here. We know that H of S is equal to V naught over VI. So we're just going to use the voltage divider formula. And the voltage divider formula says that, well, we have some V out and it's equal to some V in. And this is for a circuit that looks like this. And then it's being multiplied by the resistor over the V out. And we know that this is the resistor over V out as it's in parallel with it. So we can just say plus minus V out over here. So we are going to have R right here up top. And then on the bottom we have to have the other resistance or impedance plus this resistance again. So the other resistance is going to be this R1. And then we're going to have a plus S times R inductor. And then we have plus R. Now we do have values for these that were given. So we can plug these in now. We have 127, and this is all over our R1, and our R1 is 75, plus the inductor, which is 10 times 10 to the negative cubed times S, and then we have a plus 127. So we're going to add our constants together, and if we do this, we're going to get 127 divided by a 202 plus 0.01 S. And that's just if I write this out. We need to get S by itself for this answer. We see that S needs to be by itself. So to do that, we are going to multiply the top and bottom by 1 over 0.01. And then if we do this, we're going to get 1270 or 12,700. And then this is over 20,200 plus S. And so this would be our answer. That's going to give us that answer. Now, let's look at for part B. At what frequency will the magnitude of H j omega be maximum? Well, I'm going to write part B right here in red so we can see it's totally opposite. If we plug in, we know that S is going to be j omega. So we're going to say j omega is equal to, we have this 1270 divided by, I don't know why I keep saying 1270, it's not 1270, it's 12,700 plus j omega. So the S is, the j omega is inputted where the S was. And so looking at this, well, we know that if the denominator is smaller, the numerator will be bigger when we divide. We don't want to mess with it, so it'll be at max when our omega max is equal to 0. So that's how we get 0. Next we have what is the maximum value of the magnitude of H j omega. The maximum magnitude we know is 0. So we're going to say that j omega is equal to 0. We're going to have H of 0. And this is equal to our 12,700 divided by our 2,200. And then we have a plus 0. But this means that if we were to convert this into the polar form, because right now it's in rectangular form, we would just need to add angle 0, 0. And to get to polar rectangular form, you would just use the equation where you have the Vmax, or the magnitude, this would be the magnitude, square root of the real number squared plus the imaginary number squared, and our angle is equal to the tangent -1 over imaginary over a real number. And so in doing this, for here, we are going to get 0.629 if we divide them. And we can see that that will be the answer for part C. Now, in part D, we're going to look at this, and it asks us what frequency will the magnitude equal its maximum value divided by the square root of 2. So we're looking at the frequency H j omega, and we're looking at C, and we're setting this equal to the maximum divided by the square root of 2. So we'll have our H max divided by the square root of 2. And on the left, this part is just going to be this part, what we found earlier. Except we're going to be replacing this with omega c. We're going to say that we have a 12,700 divided by, we have 2,200 plus omega c, and this is equal to our H max, and our H max we found to be this 0.625. So we're going to say this equal to a 0.629, sorry, not 5, 9, 0.629. And it's asking us divided by the square root of 2. So this is divided by square root of 2. This is in magnitude, and this needs to be in magnitude. Currently, it is in the rectangular form. We don't want it in the rectangular form, we want it in the polar form. So to convert this to the polar form, we're just going to use these equations right here. Well, instead of writing all that out, what we're going to do is we're just going to, all we care about is the actual magnitude here. So we're going to have the square root of this squared. That's how you find the magnitude. You can have a plus 0 squared. And also, the reason why we're only finding the magnitude is because it asks for the magnitude here only. And then we have the square root of this bottom part. We have this squared and this omega c squared. Now, we have to manipulate this so that we can find our omega c. So basically, we would take this 12,700, multiply it by the square root of 2, divide everything by 0.629, and then square all of that, subtract 20,200 squared, and then square root all of that, and we'll get omega c. And if we do all of that, we're going to get that our omega c is equal to approximately 20,182. And so that is going to be our omega c, and that is the answer for part D. Now, we actually need to find our omega c, and this is the same value as the omega h max square root of 2. Same exact value because of this omega c that we're finding right here. And so that will be the same answer for part E. Now we're going to look at part F. We're going to examine the transfer function magnitude and phase as the frequency varies. So as the frequency varies, we're going to get slightly different answers. We have when j omega is equal to 0. And so this is very similar to what we've done earlier, where we have this right here, where our j omega is equal to 0. So it's really going to be the same answer. It's going to be 0.629 at an angle of 0 degrees when we're looking at h of 0, because the magnitude here is 0. And remember, when we do these together, we're going to divide the actual numbers and then subtract the denominator angle from the numerator angle. So we get 0.629 at an angle of 0 degrees. Now we're going to look at part G. And in part G, we have h j omega is equal to 0.3 times our WC. Well, this is our WC. So we're going to have 0.3 times this. So we would write this out like this. And then we need to incorporate this into our actual hj omega. This is going to be 12,700 at an angle of 0 degrees initially. And this is being divided by our 20,200. And remember, we need to find the polar form, but we can't just plug it straight into there. We need to plug it into here first, because this is the rectangular form. And our j omega is this, and we can only plug it in the rectangular form. So we are going to have plus j. These multiplied together is going to give us 6,054.6. And then if we plug this into a calculator using the rectangular to polar conversion, we are going to get 12,700 with an angle of 0 degrees divided by 21,087 at an angle of 17 degrees. Make sure you check your angle. This is correct, but you would check it by graphing the real number and imaginary number, and it would be somewhere in this quadrant. And we can see that 17 degrees is somewhere in this quadrant. So we're going to divide the real numbers and we're going to subtract the angles. And so we would get 0.6 at an angle of 17 degrees, negative 17 degrees from this, because we're subtracting the bottom, which is the 17. Now we can look at part H. In part H, we have something very similar. We just have it in the polar form without it being multiplied by the 3 right here, or the 0.3. When we do this, we are going to have H, our omega c we found earlier, right here, as 20,182. And so when we plug this in, we're going to set this to 12,700 at an angle of 0, divided by our 2,200 plus j 20,182. So putting this into the polar form from the rectangular form that we currently have it in, we're going to get 28,554 with an angle of 45 degrees. So dividing the reals and subtracting the angles, we're going to get approximately 0.445 with an angle of negative 45 degrees. So this is the answer for part H. I don't know if I wrote the answer for part G, but you can see it's 0.6 at an angle of negative 17. And so those are the answers there. Now we are going to look at part I. And in part I, we have H, where we have 3 times our omega c, and our omega c is 20,182. So this is really repetitive, but it's important because we are testing it at different frequencies. So we're going to have the top be the same, obviously, and then the bottom first part is the same, but we're going to have plus the imaginary number at 60546. And then if we convert this, again, using the previous mentioned polar rectangular to polar equations right here, we are going to get a 12,700 angle of 0 degrees, and this is over 63,826 at an angle of 71 degrees. Divide the numbers, subtract the angles, and then we're going to get 0.2 at an angle of negative 71 degrees. And that's how you would go about solving for this problem or something that looks like this.